Okay, so let's get started. So today we're going to finish up with our Whirlwind tour of the various topics that we're going to be covering in this class. Today we're going to be hopefully quickly covering wavelets, low-dimensional embeddings, and a little bit of persistence and homologies. So a little bit of computational topology. Of course, you should still stop me and ask questions if you're confused. The goal is basically just to give you a flavor of what it is. We'll be going through this all in rigor later. Especially for our persistent homologies, we do not have time to actually tell you exactly what we're doing because that would be an entire lecture and will be an entire lecture near to the end of the semester. So last time we left off on wavelets. So we finished off with these random graphs, and then I switched topics completely to talking about wavelets. So many of you will hopefully have heard of the Fourier transform before. So basically that is giving it's a basis for the space of functions in terms of things like sines and cosines or complex exponentials, which are of course equivalent. But now, what happens when you try to take the Fourier transform of a very localized function? So like if you have lists on the left there, you have just a single square wave, basically, right? So it just goes up and then goes down, and it is the support for that function where it's non-zero is very, very constrained, right? So somehow the function is local in time or space. So it's very local. But when you do a Fourier transform of that, well, what happens? In order to approximate that function, the Fourier components, well, they span the entire frequency spectrum because the basis functions contain information that's localized in frequency, but not in space or time. And so therefore, it's hard to represent discontinuities. I mean, you can still approximate them, but it's hard and it requires lots of information. So now, this was the motivation behind the construction of wavelets. Basically, Fourier transforms give you a basis for the space of functions in terms of these periodic functions, sines and cosines, but that doesn't work so well for really localized functions. So can you come up with a basis for the space of functions that really is local in some sense? And well, the answer is yes. And one way of doing that is these things called wavelets. So you want to find an easy to compute with orthogonal basis set of functions that have finite support. And the finite support makes it easier to represent functions that have discontinuities or that, well, just only occupy some small region of space. And it should be simple pieces. Like part of the reason we like sines and cosines is because they're simple to reason with and work with. So the basic idea behind most wavelet constructions is this idea of dilations. So dilations are these mappings that scale all distances by the same factor. So you can think of it as like just shrinking things for the most part. And a dilation equation is a function that is defined in terms of linear scaled versions of itself. So for example, if we have a function that's defined f of x is equal to f of 2x plus f of 2x minus 1, well, that is a dilation equation that can be satisfied by just this constant function on the interval between 0 and 1. And then, well, f of 2x is just the constant function on the constant 1 function on the interval 0 to 1/2, and f of 2x minus 1 is the constant 1 function on the interval 1/2 to 1. I think I got those backwards. But basically what you can do is you can define a dilation, you can define a function that is built up of pieces of itself that are scaled and smaller. And that's the basic premise behind these wavelets. There are other ways of doing this. So this is a slightly more complicated example where you have this f of x function is equal to 1/2 f of 2x plus f of 2x minus 1 plus 1/2 of f of 2x minus 2. So basically what you're saying is that if we started with this triangle function, you can get that triangle function by taking a smaller triangle, another smaller triangle, and another smaller triangle and adding them together. And so these are dilation equations intuitively. And when you have a dilation equation and a solution to this dilation equation, so you have some function that satisfies this dilation equation, well, you can define a 2D set of scaling functions. What do you mean by a 2D set? Well, we mean that for every one of these functions, you can scale it. You can scale it down and you can shift it. So that's what we mean by 2D set. So you have the shifting of the functions as well as the scaling down. So like in the previous example there, for this first example here, both of the copies in this first example were scaled down by 1/2, and then one of the copies was shifted over. So that's basically how we construct this 2D set of scaling functions by these shifts and these scalings. And you'll note that for any particular j in this particular case, by this definition, what we've done is that is the all the family of that set of scaling functions that has a particular scale. So all the things that are 1/2 of the original scale, or 1/4 of the original scale, or 1/8 of the original scale. And these span some space, since, I mean, they're functions, they span some space. And if you satisfy the particular dilation equation of some particular form, then each of the things at a particular scale level are a linear combination of the functions at the next scale. So obviously you can construct from the things at one scale the things at the finer resolution. Okay, so that's the basic idea, is that by moving on to the next scale level of these functions, you can then construct the previous scale functions. So each of these spaces are contained in each other, function spaces. And so if you want to approximate a function then, well, you can sort of like with Fourier components, where you can just cut them off. So you can have a filter for the high frequency components or whatever. You can filter out the wavelets by just choosing a particular scale level that you want to approximate your function to, and then using that set as the basis for your for approximating your function. So we will be talking about the Haar wavelet in a little bit more detail. This is one of the most basic wavelets that people talk about. And you start with this this basic idea of just having this constant function. So that's obviously the function that is constant 1 between 0 and 1 is a very simple function, and 0 everywhere else. It's a very simple function that has support between 0 and 1. And of course, you can construct it out of 2 scaled copies of itself. And so what you do is at level 1, you just have these, you have the unscaled copies. You have one here, one here, one here, as you shift them along. At level 2, well, you have the ones that are half as big, and you have twice as many of them going along. And at level 3, well, then they're each a quarter as big, and you have more of them, etc. And you can pretty easily see that you can approximate a function this way by, this is basically just approximating a function with rectangles of different sizes. Because you can use these as a basis and just scale up them up the appropriate amount. So there are a couple of issues with doing this though. One of them is that, well, these aren't orthogonal. So we might want to reduce the linearly independent set. So we don't want, like, because they're not orthogonal, because clearly, well, you can construct some of these functions from other ones, right? And so you can reduce down to a linearly independent set. And then you sometimes also want the property that the integral of these functions is 0. So that just happens to make life easier. So instead of just having something that is above like this, you define a slightly modified function that is up for the first half, and then, sorry, is 1 for the first half and -1 for the second half. And this is basically what the Haar wavelet. So it's this family of functions together. There's some way of making sure that you have an orthogonal basis set of these things, the same way that you have an orthogonal basis set of functions of sines and cosines for a Fourier transform. And this is just another way of decomposing your function. And this has its advantages and disadvantages. One of the big advantages is, of course, this locality. And so these have a number of different applications, ranging from things like data compression, signal processing, just lots of like really signal processing and communication type of applications, where really you're sending a signal, but that signal, well, it's not completely periodic. Like there's be no point in sending a completely periodic signal, but you want to encode variations that are localized in time. And so that's how often signals are sent. And of course, there are issues with designing a specific wavelet system. So we just gave one particular wavelet system, but unlike Fourier transforms, what we've done here is we defined an entire family of different possible wavelets to build up your function. And so for some applications, particular wavelets might be better than other ones. Oh, and sometimes you also want things that are relatively smooth. So obviously, well, very few functions are as smooth as sines and cosines, but there are functions that are more smooth than the Haar wavelet, which is very, very not smooth. And so just there are other properties you can try to optimize for as you're trying to design a wavelet system. Any questions about that? So I realize this was pretty fast. We will have an actual section on wavelets later on in the semester. But if these things seem cool, or if you're just into like this kind of signal processing, maybe that's be an idea for some kind of project. Okay, so let's move on to a slightly different topic. So I'm not going to spend too long on this because in order to like do anything non-trivial, it would involve a lot more math. But the basic idea is some of you may already be familiar with things like SVD or PCA. And so these allow you to reduce the dimensionality of some high dimensional data set by just projecting it down linearly, right? So basically what you're doing is you're taking some, say an actual 2D plane, putting it in your hyperspace, and then projecting everything down to its nearest point on that plane. And so that's roughly speaking what you're doing when you're using linear dimensionality reduction. But what if your data set's actually nonlinear? So this is a classic example here. This is the Swiss roll, where you basically have a manifold of points that is going around like a Swiss roll, going around like this. And so when that happens, like there clearly is some inherent like directionality to it. So it's going around this curve, but it's nonlinear. And so a technique like PCA won't let you get it because, well, no matter what plane you use to cut through it, you're not going to approximate this actual manifold that's going in, that's spiraling in space. So what techniques do we have to reduce dimensionality while preserving that kind of structure? And there are a number of different ways you can do this. So for example, you could say, oh, well, I don't care about global structure anymore. I just care about like locally being two-dimensional. And so maybe you could do some sort of manifold learning or approximate some low dimensional manifold, and that would give you some low dimensionality reduction. Another way is to say, well, maybe I only care about pairwise distances, but I care a lot more about the things that are close together, and things that are far away, well, their distances don't really matter anymore. So I'm just going to try to construct a 2D picture where things that are nearby in the picture are nearby, but things that are far away, the distances might be really wrong. There are a number of different techniques that people use for this. TSNE and UMAP are some of the more common ones that I see. It depends a little bit on your subfield, what dimensionality reductions they tend to use. But nonlinear dimensionality reductions are an open area that a lot of people still work on. These different techniques often have different inspirations. So for example, UMAP is said to be inspired by concepts from algebraic topology. I still need to take a closer look at the algorithm. I haven't looked through it in enough detail to know exactly what that connection is, but I'll look through that paper, and that might be one of the things I present later in this class. But that, of course, brings us to our final topic, which is some applications of algebraic topology. So now, this is one of those things that people have been working on for the last couple of decades, is trying to find applications of algebraic topology. Now, of course, algebraic topology tends to be one of the more pure fields, but people have been trying to take topological statistics to analyze actual data sets. So what kinds of topological features are we talking about? Well, we're not talking about anything too advanced. We're only basically talking about high dimensional holes. That's really it for most of persistent homologies. And the basic idea is you represent a data. How many of you know what a simplicial complex is? Okay, so a few people, but so you guys all know what a graph is now, right? So a graph is basically you have a bunch of points and you have some edges, right? And so you can represent something like this by having two different sets. One is your set of vertices, one is your set of edges, right? And you can really think of edges as just unordered pairs. Sorry, talking too fast. But you can really think of edges as just unordered pairs of vertices, right? That's what an edge is. How would you generalize this to higher dimensions? Well, you might say, well, instead of just having a pair, maybe I also want triples, right? So maybe I include something that I'm going to call, let's say I'm going to call it F for like faces. And this is going to be equal to triples of vertices. And maybe that corresponds to this triangle face here. And so if you have a triple, maybe that also means they also have the edges like, and I'm not going to go into detail, but basically some procedure like this lets you generalize graphs to simplicial complexes. And so what we're going to do is we're going to first start by having a cloud of data points. So maybe we have points here, 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 and here. And you have some distance function. So maybe you're in Euclidean space or wherever. So you have some distance function between points. And then what you can do is you can say, well, if things, oh, what just happened? If things are close by, well, maybe we'll link them up with edges, okay? And maybe if things are far enough away, maybe you won't link them, but maybe there's a point here and you link these things together, okay? So you link things up together with edges, but then you also have some rule, roughly speaking, for linking things together into faces. One way of seeing this, and one that's commonly used, is maybe if you start with this point cloud here, what you do is you start with some radius. You take each point and you put a radius around it, a hypersphere around it, and then you slowly increase that radius. And as that radius increases, you'll see that these spheres merge. And when these spheres merge, that means that those things are now connected, basically. Does that sort of make sense?
Merge or like just overlap?
Overlap. So when I say merge, I mean like there's no longer a space between them. So once the two spheres get bigger, well, they touch each other, right? And then all of a sudden, you don't have any like empty space in between them. And so like the simplest one is if you have 2 points here, as they get bigger, you start with two connected components, right? You have this connected component and this connected component. As they get bigger, as you put bigger and bigger circles around them, all of a sudden you only have one connected component. And so that's what I mean by merge. So the data clouds merge into each other in some pattern. And when you start having these things merge in together, well, what happens then is you end up with some topological shape, or I mean, you end up with some shape, right? And this shape has topological quantities because maybe as points are merging together, well, that's a bad example, but let's say as these points all merge together, maybe you're left with some hole in there in between. So you're left with an actual like hole in the merged space. And this roughly corresponds to having a hole in the simplicial complex. So there's some way of making this formal, which I'm not going to do right now because that's an entire lecture. But then what you can do is you can ask questions about the simplicial homology. So basically, how many high dimensional holes of different dimension do you have in this data cloud as the radius expands? And so that corresponds to some kind of filtration on the simplicial complex. And some of these holes stick around for a long time. And somehow we think that these things are meaningful. So for example, if you go back to the very simplest very simplest case of just connecting components, maybe the fact that you have a bunch of points here and a bunch of points here, well, you note that these points all quickly merge together, right? But the fact that there's separation between those two data clouds, that persists for a long time. And so somehow that implies something about our data set because it has two connecting components for a really long time. And that's basically what persistent homology is measuring, roughly speaking. So you start with these discrete points, and then as you expand these radii around them, some features, some types of high dimensional holes or high dimensional structures remain for a long time, and that says something about our data. What it says, we don't always know, but it says something, and then maybe you can use that to distinguish different types of data from each other. Okay, I included a lot of math here. I'm not sure how much of this I should go through because I am not going to go through most of this right now. It'll be in the notes if you want to look at it, and of course, like we will go through this in detail later. But the basic idea is that this has to do with simplicial complexes and the topologies and homologies on top of them. So you're basically computing the Betty numbers of the simplicial complex, which we will talk about at the end of the semester. Yeah?
In the previous slides, you mentioned like things like manifold learning, or the techniques where you can just learn the global like
Yep.
manifold structure. Is there any reason to use this over those other techniques?
I mean, when is there ever a reason to use one technique over another technique? And so that is one of the standing questions about persistent homology is it actually useful? And that there are some well-respected scientists who think that it is actually useful, and they've run it on some actual data and shown that it picks up on signals that regular machine learning techniques or manifold learning for some reason don't right now. Could you learn it from those things? Maybe, but like this is one way of approaching it, and this way also has a lot of beautiful math. And so there are a lot of mathematicians who really like thinking about this problem and trying to apply it. Doesn't mean it always works. It often doesn't work, and it also turns out to be hard to compute on because, as anyone who's taken topology knows, computing topological invariants can be hard. So the answer to that is, well, we don't know. This is still very much a research method. People have been trying to use it. There are software packages you can use and download that would just be like, oh, I'm going to compute all of the first Betty numbers of this data set. And so you can do that. And you can feed that information into some sort of statistical classifier. And sometimes you get useful stuff out of it, sometimes you don't. it's hard to know a priori. But that's true of a lot of data science methods. It's hard to know a priori what will work and what won't work. Sometimes, well, sometimes you know things that definitely won't work, but it's hard to know what things will work better. Okay, I'm not going to talk about all like group theory and topology. Here are some pretty pictures I got from the internet, just to give you a flavor of what's going on. So basically, it's what I was saying. This is just looking at connected components. You can also look at loops and higher dimensional holes. So as, does the animation work? Ah, okay, there. So as this animation is going, you're expanding a little ball around each of the data points. And then as those balls merge, you lose connecting components. And what the right-hand side diagram, it's a persistence diagram. It basically asks, when is a connected component born? So when does a connected component first appear? And those all appear at time 0 because you start off with n connected components if you have n points, and then they slowly die as they merge together. And so that's basically what this persistence diagram is showing. You can do the same thing for higher dimensional holes. 0-dimensional holes are not particularly interesting. You can get those pretty easily since those are just the connected components of your graph. But these higher dimensional holes are sometimes a little bit more interesting. So actual 1-dimensional hole in this disk of points as the radii increase. And of course, you can have higher dimensional analogs of this, though in practice, they're hard to compute. And so often you only work with the first couple Betty numbers and not any of the higher ones. There are also things you can do with like signal process. Oh yeah, go ahead. Yes, so at least in the default way of doing things, you grow all the radii at the same rate. Yeah. Another thing you can do is you can also apply these sorts of ideas to things that aren't just data clouds. You can also apply them to continuous signals. And here you're basically just doing a thresholding and seeing how many connected parts of your signal graph you see. And somehow you can use this for some sort of compression, because then what you're seeing is connected components disappear or appear based on like big shifts in the direction of your signal. And so the mathematics for this is actually pretty similar to the mathematics of the data cloud points. So obviously it has a very different flavor.
For this one, can't you also use more Morse theory?
Oh yeah, so there are a ton of other good signal processing methods you could also use. And like I said, one of the big open questions is, are you getting signal from lists that you can't get using other ways? And so personally, I am not convinced that I haven't seen any super convincing examples where persistent homologies are just like much, much better than using other more standard methods, but there very well could be. And it could also be just because right now we can only really compute the first couple Betty numbers. And so we can't actually compute any of these higher order topological constants. And maybe if we could, then we would be able to see things that are radically different than what normal machine learning methods do. Right now, there are methods that use topological data analysis that are comparable to state of the art in very specific domains. And so those are quite cool. And there are some nice papers on that. In general, if you were to ask me what I would recommend, I would probably recommend you use a more standard tool unless you care deeply about the math. But this is a graduate math topics course. And so there are this is one really cool way of trying to apply algebraic topology to real data sets. And it's a young enough method that I really do think the jury's still out, and it's quite possible that there will be like some killer application. Yeah, so applications. So you can do compression of signals and images by only storing a persistence diagram. So basically keeping track of when things go up and down. So these sorts of critical points. You can also use these sorts of persistence diagrams as an additional feature that you're plugging into some sort of machine learning pipeline. So you might ask, well, what am I getting that is that you don't just get from running a convolutional neural net on your data? Well, the answer is, well, maybe you aren't getting anything else. But if you have a big enough machine learning classifier, you may as well throw all the features in there and have it learn what's important and what's not. And that basically is the end of my big overview of these different topics. So do you have any general questions? So for your projects, for the end of the class, you should pick some topic that you're interested in and like try to either apply it to some data set. There are plenty of data sets out there, or maybe you can pick some like interesting problem and try to use connect together different tools to try to solve it. So like maybe you have some algorithmic problem that you care about and you want to play with different types of hash functions. Or maybe you have some interesting biological data. Sorry, I'm a computational biologist, so I keep on thinking in terms of biology. But maybe you have some cool genomics data set that you want to try to apply persistent homologies to. And maybe it'll work and maybe it won't, but something along those lines. Any questions about any of this? Okay, great. So that is the end of our Whirlwind overview. Now let's get back to, well, math. Or, I mean, in this case, I guess theoretical CS, but something close enough to math.